Hello, colleagues. Welcome to another session where we are discussing transportation problems. Okay, this is a special type of linear programming problem where the objective is to minimize the cost of distributing a product from a number of sources or origins to a number of destinations. So transportation problems are a little bit vast, and we are looking at them from the angle of operations management or decision behavior. And we're going to have a series of them where we are going to go in depth into the methods and why we basically look at transportation problems. Okay, so here basically what we are saying is that you have a number of supply centers and destination centers, and basically you are trying to find the minimum or the barest minimum cost that it will take you to transport your particular products from each of those destinations from each of those supply centers to your destinations. Okay. Because of its spatial structure, the usual simplex method is not suitable for solving transportation problems. These problems require spatial methods of solution. Okay, we know previously in the previous videos that we looked at linear programming. We looked at the method of simplex, where it has a particular unique structure that involves the tableau and all that. In this case, because of the structure of the transportation problem, we might not be able to use that particular method of solving. All right. Let's move forward and look at the destinations and suppliers we are talking about. Okay, so in this particular table, we realize that there are on this side of the table or the structure, we have supply centers or sources, and on this side of the table we have destinations. Okay, so basically you are looking at this particular supply center being able to supply to three particular destinations. It should be able to supply to this one, and to the up to the nth demand center or destination center. All right, so this particular supply center has a limited number of products it has, so we can say 50, and each of these could have each specific 70 and maybe 100 on the last one. Okay, and these destinations also require only a limited number of products. So maybe this particular destination can only need 25, and this guy can only need 35, and this one will need maybe 150. Okay, so you need now to analyze how much will it cost you to transport from supply 1 to destination A or destination 1, and how much will it cost you to supply from supply 1 to destination 2? How much will it cost you to supply from destination 1 to destination N? Okay, and basically you prioritize those that give you the lowest cost, and then later on go to those that have a higher cost of supply. Okay, having introduced that, we are going to look at this particular problem here. This is a table giving you the demand and the supply. Basically, on this side is these are your supply centers, and basically what you have, your A, B, C. These give you the demand. Okay, so you have 70, 90, and 180 as your demand, and basically 1, 2, 3, 4. Having those particular digits on the other end, 50, 80, 70, and 140 are your supplies. So basically, project A or supply center A can distribute to A, B, C, and supply 2 can distribute to A, B, C, D, and the like. And basically, these figures that you have in this table are basically your cost of transportation. Okay, so basically what we are saying is that supply 1 can only supply 50. Okay, while demand A or destination A wants or demands this particular number there, 70. So supply 2 can only supply 80. Okay, supply 3 can only supply 70. That's all they have in their factory. Okay, and demand B or the store, which is B, store B, only wants an inventory of 90. So basically now you begin to distribute from these supplies to these stores. Okay, now having explained all that, how then do we calculate? How do we find the optimal? The whole logic here is to find the optimal amount, the barest minimum amount it would cost us to distribute everything that is wanted by the demand from these supplies. Okay, and we have two types of transportation problems. We have balanced and unbalanced transportation problems. Okay, so balanced transportation problems is where your supply, how do you write supply? Supply equals demand. Okay, this is where supply equals demand. This is a balanced transport problem. Okay, then unbalanced, basically it's the opposite of this. So where you have your supply not equal to your demand. Okay, so we are going to delve deeper on how we deal with each of these. Basically, you realize that when it is unbalanced, we are going to introduce what is called a dummy column, and we work it out as though it were a balanced particular problem, okay, a transportation problem. But we are going to reach there when we reach there. So let us try to solve this. And there are different methods, basically, that you use to solve this type of linear programming problem. Okay, we have the northwest corner rule or method. We have the row minimum method. We have the column minimum method. We have the least cost method. We have the VAM, which is otherwise called the vocal approximation method. Okay, and we are going to look at the prominent methods as we go on. Okay, so now we are going to start with the northwest corner method. Okay, we know that our northwest side, if we are looking at the compass, is this particular side. Okay, so this rule says that you start working out your problem from this particular direction. Okay, basically you have these different corners, boxes that are representative of the cost. Now you begin allotting from the northwest corner. So basically the first corner that you begin allocating is this particular corner, which is your northwest corner. Okay, so basically if we are saying that you are starting from this particular box here, you are looking at supplier 1 distributing to store A. What does supplier 1 have? 50 in factory. In the factory has 50. But what does this guy need? The store A. He needs 70. So basically we know that supplier 1 can distribute everything that demand A wants. So we say 50. So when we give 50, we know that then you have depleted everything that demand A wants. So you have a zero supply there. But if you have given demand A 50, meaning they will still need another 20 remaining, isn't it? Okay, so if that is the case, you proceed, you cancel out this because this guy can no longer supply on this side. Okay, then you go to the next. What is your next northwest box? You realize that your next northwest box, since this one has been eliminated, you have this one where there is a 3. Okay, so meaning you are dealing with supplier 2 and destination A. So supplier 2 has 80 in store, while destination A still needs 20. So you give the 20 that this guy needs, and he no longer needs anything. When you remove 20 from this supplier will remain with a 60, isn't it? Okay, let's continue. So if you have depleted this guy doesn't need anything. So what is your next northwest box? You realize that your next is the 3, this particular box here. Okay. Okay, so you are dealing with B, demand B and supplier 2. So, okay, demand B needs 90. What does supplier 2 have? Because he gave out 20 to store A, he only has a 60. But the supplier B, demand B wants 90. So let's give the 60 that is remaining. Okay, what will remain then will be this side you'd have depleted this particular supplier, but the demand, so 60 from the 90 that is needed, you have 70, 80, and 90, so you remain with the 30, isn't it? Okay, so what is your next northwest corner? It is this box with a 4, right? Because you are done away with the other one. Okay, so you have demand B and supply 3. Okay, so supply 3 has 70. This guy needs 30. So you give the 30 that this guy needs. So you supply 3 will remain with it's a 40, isn't it? Okay, we continue. So meaning we are done away with this particular B because B can no longer want anything. So we go to supply C, this particular box here, which is your new north west. Okay, so this guy wants 180, but this guy only has the demand 3. I mean the supply 3 only has 40 remaining, isn't it? So when you give 40 to C, you give 40 to C. How many will this guy still need? He will need 140, isn't it? Okay. So when this guy, the supply 3 gives out the 40, he will no longer have anything more to give out. So meaning you remain with only one box to deal with, which is this particular box, which is supply 4. And supply 4 can supply 140. But what does demand C still need? He's still remaining with the 140. So you realize that the 140 is exactly going here. So that demand C no longer wants anything. So you have a 0 there. And this guy has given everything. So you have a 0. So you notice that after distributing all of them, they'll all have 0, 0, 0, 0, 0. And you have 0, 0, 0 there. Okay, you have distributed everything. And basically that is the logic about the northwest corner method. But then we are not ending here. You are supposed now to sum up the costs that you have. So in box A, you have the cost of 2 and you have supplied products of 40, of 50 quantity, 50. Okay, so let's start summing up everything now. Okay, so we are saying that the total cost is the summation of the number of products times the cost. So basically, you notice that 6 boxes are allocated. One, 2, where is it? Okay. 1, 2, 3, 4, 5, 6. Okay, and these 6 are allocated. And so for the box of 50, this particular box has a cost of 2. So you multiply 50 times 2. And the second box, you have 20 times 3. And you keep on, and you realize that 50 times 2 plus 20 times 3, 60 times 3 plus 30 times 4 plus 40 times 7 plus 140 times 2. And that is giving us, it gives us 100, 1,020. Okay, whatever currency we are using, we didn't indicate the currency, so maybe we can assume it's dollars. Yes, dollars. Okay, so basically that's that. See you in the next class.